So in the last lecture, we went over a few points. The first point was to discuss what is the role of StatMech. It was and that was to ask how to, given your interactions at a certain length scale, how to predict the behavior at a larger length scale. And when we do this procedure, I gave some examples of how new phenomena come, new emergent concepts come, which are not predictable when you do the microscopic scale. And then to understand one example we worked out to understand how when we change the number of particles, some of the macroscopic quantities become well defined. So to do that, we took a gas and took a small volume inside the gas, and then you asked, if I measure density in this volume, when does it become well defined? So, and we showed that as you increase the delta V, it becomes, the value of density becomes, let's say, more concentrated. Okay. So, so today so I realized that it is better to do, I was a bit, from the questions I heard, a bit unclear about some of the things that were done. So I'll just redo some of the calculations a bit more precisely so that what is meant I will clarify. And then today we will spend on probability a little bit, the law of large numbers, central limit theorem. So it won't have anything much, just to give a background of what happens when numbers become large. So I'll use the board sometimes and sometimes the slides. So let me quickly tell what we were doing last time. So we took a volume delta V and asked what is the probability that there are k particles in that volume, and we showed that that answer is the Poisson distribution, lambda to the power k by k factorial e to the power minus lambda, where lambda is the mean number of particles in that volume. Okay, rho is the mean number density, rho times delta V is the mean number of particles that will be there in delta V, and k is discrete, runs from 0 to infinity. And then lambda could be large, small. So we did an estimate of, if I take a small millimeter cube volume, how many particles are there, and lambda happened to be order of 10 to the power 15. So it made sense to look at lambda, which is much larger than 1, which corresponds to saying that rho times delta V is much less than 1. But rho is a number density, so if I associate a cube of size L cube with each particle, then rho is like 1 by L cube. Okay, so when lambda is much greater than 1, it means that your measurement volume is much greater than the interparticle spacing. So you have many particles there. Then we derived two particular moments for the Poisson distribution. One is the mean value of k, which is lambda, and the other one we derived was mean value of k square, which happened to be lambda square plus lambda. And then quickly we did k square minus k average square to be lambda. But why are we interested in this particular quantity of second moment minus first moment square? What is so interesting about that? So if I take a generic distribution P of x for some variable x, it has some, let's say it has some distribution like this. So there's a mean value x, which is somewhere near the peak. It need not be at the peak value, but somewhere. Then what you're interested in sometimes is how much does x vary about this mean value. So every time I take a realization, I could get a value of x here, x here, x here. On average, it is x bar, average x, but it could fluctuate. So one measure of how much x varies from x bar is to look at the quantity y, which is the difference of x minus the mean value. Okay. And then the mean value of y is 0, because if I take expectation value of y, this expectation value of x minus expectation value of x, which is 0. But if I look at the second moment of y, it is, I take the square of this, which is x square minus 2x x bar, and it's x bar square, and there's an average over the whole quantity. Now, the average of a sum is a sum of the averages. But so when I take the first average, it is x square. The second average is 2x. This average becomes x bar average square, and this remains as it is. So when I take the second moment of this, it becomes x square minus x average square. Okay, so that is why we are interested in this quantity k square minus k average square. It is just saying that how much does a quantity typically fluctuate from its mean value. Okay, so given that, so I come back to this is just repetition of that whole quantity. I look at k square minus k average square, which is lambda. So what do I know? So I say that my typical value is lambda, but if I look at the variation difference from the mean value, it is order of root lambda. So it makes sense to define x equal to k minus lambda, the difference from the mean value. And I know that if I take the second moment of this, it is lambda from this particular expression. Therefore, your typical value of x, typical value means when I measure x, what do I get? It will be order root lambda. I take the square root, I get root lambda. So that is why, so the mean value is x and mean value is lambda and the fluctuation is root lambda. Is this point clear? So then we need to ask, how do we do an expansion? So if I know that the typical fluctuation is root lambda, then it makes sense to write that I keep my x by root lambda is some variable y. So I say x is y times root lambda. Okay, so now let me do on the board. So I have some quantity p of k. Okay, and we are defining a variable x, which is k minus lambda, but this quantity by root lambda. So we are defining, I will call it y because we used. So we are saying that k minus lambda, the typical order of magnitude is root lambda. So I divide by root lambda to get a variable y. So if I look at, so somebody asked the question that k was discrete. So what about y? Is y discrete or not discrete? So the k is discrete by k. So if I take the difference between two values of k, delta k is 1. So if I look at delta y is 1 minus 1 by root lambda, which tends to 0 as lambda tends to infinity. So even though k is discrete, when I take y, which is scaled variable y it behaves like a continuous variable. Okay, so when I talk about p of y, it becomes a probability density function with integral dy equal to 1. Here it becomes summation over k, p of k is 1. So that is why it became from a discrete variable to a continuous variable. Now let me expand with this definition. What do I get for, so I want to find probability of y, given probability of k. So first let me do a dump expansion. I will do probability of k is equal to lambda to the power k becomes lambda plus y root lambda e to the power minus lambda the whole factorial. Right, this is my, so what I have done is I have taken this p of k and I have put for k y root lambda plus lambda. Now lambda is large, y is finite. I can do an expansion for large lambda. So let me write again Stirling formula. So n factorial is root of 2 pi. Okay. So all I have to do is replace this with this formula. So probability of k equals lambda so there's a root of 2 pi, then there's e to the power n, so that becomes e to the power lambda plus y root lambda, and n plus half. So we are now going to do an expansion for large lambda, keeping y fixed. So I pull out this lambda is common. I can pull out a lambda. So I get lambda to the power lambda plus y root lambda, which cancels with this one. So I get 1 by square root of 2 pi lambda. Then this e to the minus lambda cancels with this one. I get e to the power y root lambda. Remaining is 1 plus, so there is something remaining here, which is e to the power minus of lambda plus y root lambda plus half log 1 plus y by. Is that clear? I have just exponentiated this y 1 plus y by root lambda. Now this is equal to two pi lambda. Here I do a Taylor expansion. This becomes e to the power minus plus half. Remember, this is a small number. So the first term is y by root lambda. Second term is minus y square by 2 lambda plus order y cube by lambda to the power 3 by 2. The third term. Higher order terms of this order. Okay. So now I expand this and keep arranging them in order of largest term, second largest term, and third largest term, and so on. So when I multiply lambda with this, I get minus y root lambda. Then lambda multiplied with this plus y square by 2. Then I multiply a term here, which is order y cube by root lambda. Then if I multiply this one, the lambda cancels out. The next one is y cube plus y cube by 2 root lambda plus so on. Okay. In this expansion, now I put lambda to infinity. So all these terms go to 0. This term goes to 0. This term goes to 0. There's a lambda independent term here. These two terms cancel out, and you are left with e to the power, oh, this should be minus y square by 2 So that is the, so this way if you expand, then there is no ambiguity on which term to keep and which term not to keep, and it becomes clear what is it you are doing. You are looking at a variable which scales as 1 by as root lambda. Is this clear? But this is still probability of k. How do I get probability of y? So this is probability of k. Because if I integrate this over y, I don't get 1. I get a 1 by root lambda. So how do I was still working with a variable k. So how do I change variables in probability? So I have two variables, let's say k and y, and I am given that probability of k is given. Then there's a simple way of changing variables. It says it should be equal to this is just to say that when I change variables from k to y, my probability should be conserved. So if I want to go from here to here, all I have to do is I look at the expression for dk and dy, which is here. If dy is dk by root lambda. So dk by dy is root lambda. So e to the power minus y square by 2 by root of 2 pi lambda into root lambda is py of y. So this root lambda and this root lambda cancels out, and you get a nice normalized distribution. Okay, so this was the derivation I was a bit careless with, and you get a nice normalized distribution, which is a Gaussian. Is this point clear? Now, and that is what I have written. Oops, sorry. Yeah, so this is just the, whatever I did on the board, it just is contained here. And this normalization went wrong, how to change probabilities, and you have a nice answer here, which is what I have derived on the board. So what does that mean? It means that your typical fluctuations are fluctuating about the mean and is described by a Gaussian function. This is what. Now, somebody asked, you could ask why scale like this? Why not scale in some other way? So I think somebody in the audience had asked that this describes the behavior around the mean, but it does not tell you anything about how the tails behave. So if I ask, what's the probability that you will get some answer which is not order root lambda, but let's say 2 lambda. So my density is lambda, but I want when I measure, I get 2 lambda as my number of particles, which is very rare. So, so I thought that since that question came, I will try to explain what happens if you look at fluctuations which are not typical but atypical, which are rare, how to do such problems, even in the context of a Poisson distribution. Is it clear? So now we are going to ask, so let me try to tell again. So we figured out that the mean number of particles is lambda, but when I look at fluctuations, it is order root lambda. Then we then we focused on these fluctuations and showed that those fluctuations are described by Gaussian around this point. Now we ask, but what about very rare fluctuations where, let's say, there are 0 number of particles, or there are double the number of particles we normally get. That is not described by this. That is not described by this distribution. It is described by something else. So I'll tell you how to derive that answer. Okay, I think it was your question. Yeah. So let me do this derivation on the board. It's slightly more slower if I do on the board. So it's just a two-step derivation, but it takes you to some terms which are useful to know. So we again start with this expression, and you know that your mean value of k is lambda. So let us define a variable x which is lambda times x. So unlike the previous y which was scaling as root lambda, now you are now we are looking, if I keep x finite, looking at values of k which are order lambda. So let me try to, previously k was lambda plus y root lambda. So this, we are looking at values of k which is order root lambda. Now we are looking at values of k which are order lambda. Okay. So let us just plug it back in here. So you get p of k equals lambda to the power lambda x e to the power minus lambda x factorial. Wherever factorial comes, we have only one trick to do, replace it with Stirling formula. So replace with Stirling formula. So it becomes p of k equals okay. Now this lambda cancels this one. So e to the power minus lambda, e to the power lambda x by square root of 2 pi lambda into x to the power, I can put an x also here, and e to the power minus lambda x. So x to the power lambda x, I have written as e to the power minus lambda x log x. Okay. So this has a nice form. So again, if I want to convert this to p of k to p of x, I have to do the same trick. So if I were to do p of x, it is lambda times p of k, lambda e to the power minus lambda x into, did this e to minus lambda go away? Okay, anyway, into e to the power lambda into x minus x log x. Or I can derive different, or so it has a form minus 1. So I should take this e to the power minus lambda this side. Is this, so now the expansion is a bit different from what I did earlier. And it has a form e to the power lambda times something. Now so there is some technical, there is some word for this. So most of the time when you do this expansion, you will get some answer e to the power of some large number times some scale variable x. So let me first define some terms. This lambda is often called the rate, and this quantity is sometimes called the large deviation function. Why is it called the large deviation function? Because it describes the probability of large deviations from the mean. The previous one was small deviations. Now we have something called large deviation function. So so if I take log of p of x by lambda, it is x minus 1 minus x log x. Okay, and so let me just plot this answer. So now you have gone something beyond what you normally see. You have now described even the rare events even in this problem. Okay, it turns out that this large deviation function has become, even though we are just doing some calculations, this large deviation function calculations have become quite a topical problem, and there is a lot of research papers these days on computing large deviation functions, not for distributions, but for some interacting many particle problem. Okay, so it's good to know these words, that this large deviation function describes large deviations, rare events, and so one may ask, why calculate the probability of rare events when they rarely occur? So, but often in reality, things sometimes occur rarely, but they have a lot of consequences. So, for example, you could ask, what's the probability that there's a giant wave in the ocean when there are something called giant wave. The probability is very low, but once it occurs, your ship you may go down. Okay, or like asking, in this plane crash, there's a probability of 2 engines failing. Maybe that's the reason, I don't know the reason, but those small probability events are captured by this large deviation function, but the consequences may be quite, unpalatable. Okay, so let me just spend a couple of words more in this. So you have a large deviation function. I'm going to plot that function, f of x versus x. It's a simple function. Then you can ask, where is it going to be maximum or minimum? So when x is very small, how does it behave? When x goes to 0, what is the value of this function? It should be minus log x or minus 1. When x goes to infinity, or there's a sign issue here. Have I done the derivation correctly? Okay, when x becomes extremely small, what is the value of this function? You don't know. What about when x goes to infinity? Sorry? Log goes to infinity, so this also goes to infinity, but this goes to plus infinity and this goes to minus infinity. So which one wins? The second term wins, because this term is much bigger than this one when x goes to infinity. So if I were to plot, I'll get some curve which is somewhere here. What about when x goes to 0? Huh? Someone is saying that it can have only 2 possibilities. It's not. You have to take the limit. Log 0 is not defined, but log x, what is the behavior when x goes to 0? You can use some, this term goes to 0, it becomes minus 1, then there is minus x log x. Okay, so normally you do some x by 1 by log x, no? Then when you differentiate, you get this limit, x going to 0. Maybe I should do the other way around. Log x by 1 by x. Infinity by infinity. When I differentiate, I get limit x going to 0, 1 by x by minus 1 by x square, which is x which goes to 0. So that term goes to 0. This term goes to 0, you get minus 1. So there is some answer which is some minus 1. So in between, it can only do a few things. It can do like this maybe. Well, I don't know. Maybe one it goes like that. That the function looks like this. So we just need to find where is it maximum. So I differentiate this quantity. So df by dx is 1 minus x by x minus log x. So that is minus log x. And then I want to know when this is 0, it is 0 at x equal to 1. So this point is 1. And what is the value at 1? It is 0. Okay, so it is 0. So that is the other property that large deviation function always have. It has a maximum at 0. It has a maximum at 0, and the value of the maximum occurs at the mean value. The mean value occurs when x equal to 1. So this is the mean value or typical value. It is typical value. And the maximum is always 0. Okay, so that is the. Now, so this function describes the behavior for all values of your variable k. But previously, we had got a different answer, the Gaussian. Where is the Gaussian hidden in this function? That Gaussian has gone. So that was describing the behavior close to 0 here. But we were scaling it as root n. We are looking at behavior out of root n. But now we have scaled as n. So in that scale, it's come to 1 point. So this single point is what is described by what we did earlier. Okay. So we could try expanding this function about the minimum. So if I take d square f by dx square, this is minus 1 by x at x equal to 1, which is minus 1. Okay. So therefore, the function here is f of about 1 is minus half into x minus 1 the whole square. Which if you convert, so now if I take p of x, if I take this lambda this side, so p of x goes as e to the power minus lambda by 2 into x minus 1 the whole square. If you convert it to y variable, you get back the other answer. Okay. So so within this, is this sort of clear? Yes. Yeah. So it should write negative because when I take the p of x, it is e to the power lambda times f of x. And we know that the probability is extremely low. It's a rare event, the probabilities are extremely low. So this is it should be negative times a large number. So the probabilities are really low. It should be negative. If it is positive, then the probabilities become very high. So that is so the entire curve lies below the negative this line. Okay. So that was a nice example. I didn't. It also gives an introduction to large deviation function, which is normally not taught. So I think the word, if you see again, you should know what it means. That is the point. Okay. So large deviation function. Anything else to mention in that? So this is what we did. Okay, so now we will stop here. So up to now we did a very specific example of a ideal gas and its a specific question of what's the density, and we showed that density becomes concentrated as the number of particles increase. Okay. So what I thought was in the remaining class, I will do a focus on one particular aspect of what happens when you look at sum of a large number of random numbers. Now, why? In the end, I'll show you why the density calculation, pressure calculation, temperature calculation all reduces to summing over a large number of numbers which are distributed in a certain manner. But let us first do a bit more abstract and ask, if I take random variables and I sum over a lot of them, then what answer can I expect? Is there some universality that comes when you increase the number of interactions? Okay. So I will take a particular example. Why random walk? Because that also is a good system to know. It keeps coming over and over again. So let us take a simple example of what is called a one-dimensional random walk. So you have a particle which is at the origin at time t equal to 0. At every time step, you toss a coin. If it comes head with probability half, then it hops to the right. If it comes tails, that comes with probability half, it hops to the left. And the walk keeps going on and on. And so it is not deterministic, it's stochastic. The problem is stochastic. The random walker keeps moving from 1, 2, minus 1, and so on. And then ultimately you ask, after t time t, where is it? So you take t steps, then you ask, where is the particle? Now, so I can write this capital X, the position at time t, as x1 plus x2 plus x3 plus xt, where x1 could be either 1 or minus 1. So 1 with probability half and minus 1 with probability half. And now I am going to ask, what is the probability is at point x at time t? So this problem can be posed in any dimension. If it's 2 dimension, it goes east, west, north, south with probability 1 by 4, 1 by 4, 1 by 1, and so on. Okay. So is the statement of the problem clear? So even though we are posted for a random walk problem, what we are interested in is, when I add t random variables together, what can I expect for the sum? So first, some simple moments. Instead of the distribution, I ask, can I compute lower moments of this variable? So x is sum over this. This is the definition of x. If I take the average value of x, it is average value of summation over this xi. I pull out the summation, but each xi has mean 0. It's either left or right. Therefore, the mean is 0. So the particle on an average, it's at the origin all the time, average. What about the variation, variance? So variance is expectation value of x square. So I take this quantity, I square it, then I get x1 square, x2 square, x3 square up to xt square. Then I have cross terms, x1, x2, x1, x3, and so on. How many of them are there? NC2. How many pairs are there? This many of them. There's a factor 2 sitting there. To prevent overcounting, I will put j greater than I. It's just a way of writing that all the pairs together. And then I have an expectation value over that. Now, each of the xi are either 1 minus 1. No? If I take x1 square, it's always 1. So mean of x1 square is 1. So and there are t of them, so it becomes t times 1. Then there are these cross terms, 2 times expectation value of xi, xj, and summed over all of them. But the value of xi and the value of xj, are they correlated or they independent? They are independent. Every time you are tossing a different coin. So expectation value of independent events become expectation value of the product of the expectation values, and each of them we already agreed is 0. So the answer is t. Okay. Suppose, so this is an exact answer. If I know this answer, I know this answer. Suppose it was not in one dimension, but two dimension. I was adding vectors. These become xi vector, x2 vector, and x3 vector. So I'm doing in d dimensions, where it could be in 2 dimension, 3 dimension, or any dimension. If it is 2 dimensional, it is a 2 dimensional vector, and this d dimensional vector. Does this go through? First step, the mean value, it goes through because it is moving in arbitrary directions. There is no preferred direction. It is 0. Does this argument go through? Every time it takes step of order of distance 1, let us say, but in arbitrary directions. If it's 2 dimension, 4 directions, 3 dimension, 6 directions, and so on. This step also goes through because the x1 square is always 1. The cross terms are always 0 because they are uncorrelated. So this result is not true just in one dimension, it is true in all dimensions. And it is good to remember this answer. If somebody asks you a random walk, you should immediately be able to say that its variance is t after t time steps. Okay? In the sense that the particle is roughly at a distance root t in time t. Is this argument clear? Okay. Now we go back to computing what is P of x. So there are multiple ways of reaching the point x. For example, if I look at 0 after 2 steps, it could be +1, -1, -1, +1. There are 2 ways, right? So in general, if I want to compute this answer, I ask, there could be r steps to the right, l steps to the left, l plus r should be t because we are interested in t time steps, but r minus l should be x. That is the only way it reaches x. So if I tell you x and t, r and l get fixed and r is t plus, so I can just solve for this. So I know r and l, r is t plus x by 2, l is t minus x by 2. Okay. So now I have a random walk with given number of steps to the right and given number of steps to the left, and I want to ask what is the probability of doing this. What is P of x? What is it? Is the question clear? So I have derived for you how many steps to the right it should take, how many steps to the left it should take for reaching x. But what is the expression for P of x? It's a binomial distribution. Binomial because I can choose the r steps in any order. It need not be in the first r, it could be any order. So out of the t steps, I choose r of them. The remaining are left. I have no choice for the left. So that is TCR. But each step comes with probability 1 by 2. Each sequence of steps is 1 by 2 to the power t, half. So there is a 1 by 2 to the power t sitting here. Okay, so then I can do the binomial expansion. This is TCR, t factorial by r factorial, l factorial, and I can substitute to get this formula. Okay. Now I would like to do on the board the derivation of this, but next. Is this part up to here clear? Yeah, up to where is not. It's just a simple combinatorial formula. Now I want to go from here to the forward. There are many factorials here. All the factorials we are going to replace with Stirling approximation, and we are going to work with x much smaller than t. Why? Because x square is t, so x is typically root t. So in this approximation we are going to expand this formula. Okay. This is exactly the same argument we use for Poisson formula, but now it is a binomial. That's the only difference. Okay. So I should do the expansion. So let me come back here and do this expansion on the board. We will do exactly as we did earlier, so that the x So what is our P of x? Is 1 by 2 to the power t. So we are going to do an expansion for large time, but to keep, see x also becomes large, but we have to keep the limits properly. So we will do the same trick we did before. So we are going to define x is equal to y root t. So we are going to be interested in value of x, which is order root t. So once I write as y root t, once I do this, I can put it here, and now there's only one parameter t, which is large. Y is fixed. I can do a large T expansion and ask what answer I get. So, and it is always, when factorials come, it is always better to work with logarithm, because log of T factorial is better than T factorial writing fully. So log of P of x is minus T log 2, that is this term. Then there's a T factorial. Okay, so let me write the formula for Stirling's approximation. Root of 2 pi into the power n plus half. Each one of them has a factor e to the power minus n. But you notice that this plus this is equal to this. Therefore, we don't have to worry about this term. They cancel out. E to the minus t, this also is e to the minus t. They cancel out. There is a root of 2 pi here, root of 2 pi here, root of 2 pi here. So I get minus half log 2 pi. So I have to worry about only this particular n to the power n plus half term. So log of t is plus t plus half log t, then minus t plus x by 2, x is y root t, plus 1 by 2 log t plus y root t. So that was this one by 2, sorry, by 2. Then there is one more here, which is minus t minus y root t plus 1. This plus 1 is coming from n plus half plus 1 log t minus. Okay. Now we are going to get a lot of cancellation by looking at the leading term here. Okay, let us just do brute force. This is equal to minus t log 2 pi plus q. Now here we are going to do a Taylor expansion. Wherever the logarithms come, we are going to do a Taylor expansion for large t. Okay, so the first term is minus t plus y root t plus 1 by 2 into log t. So if I pull out a t, I get log of t plus log of 1 plus y by root t, which is y by root t minus y square by 2t minus log 2. I have kept up to the second term only. Maybe I should keep the third term, but it will turn out that only second term is important. then minus t minus root t into log t. So if I pull out a t here, t into 1 minus y by root t. So this becomes minus y by root t minus y square by 2t minus log 2. So remember, the expansion I'm using is log of 1 plus x is x minus x square by 2 plus x cubed by 3 and so on. And I can truncate. I should be able to show that if I keep higher order terms, they're not relevant. Okay. Now, so there are a lot of log t terms. This log t and this log t, when I add, I get t plus 2, t plus 1 plus t plus 1. So t plus 2 I get. So this cancels out some of the t's here. Okay, so I get minus t log 2 is half log 2 pi t plus 1 into t plus 1 plus t minus 1. Minus 1 plus half log t. So if I have not made any error, I get, so why it is t plus half minus t, that tt goes away, minus 1 minus half. Okay. Remaining is I have to worry about what all terms to keep in this one. So now first term I keep is I multiply t by 2 into y by root t minus y root t by 2, t by 2 into minus y square by 2 plus y square by 4t, then t by 2 into minus log 2 minus t by 2 log 2. Okay. So in the same vein, okay, let me do minus y root t by 2 into y by 2. I'm hoping I'm not making any error. This root t goes away. I get y square by 2. The next term when I do, I get a 1 by root t term. I'm not going to keep that. Y root t into y square by t, I get a root t. I'm going to drop that term. And the last one I'm going to keep is this term minus y root t by 2 log 2. When I say I'm not going to keep, what I mean is when I multiply and then I take the limit t going to infinity, those terms don't matter. And then there's a plus 1 by 2, that multiplying by this goes to 0, multiplying by this goes to 0, but it multiplies this one properly, I get log 2 by 2. Exactly the same thing I can do here. It is more or less exactly the same, so I can just write down. So this becomes plus y root t. So now I'm going to do multiplication by t plus y root t by 2 minus t into minus, so it is plus y square by 4t, t into y square by 2 into 2. Then these two will multiply to give me plus or minus plus t by 2 log 2 minus y square by 2 plus y square by 2, and this one higher order term, I don't care. This one plus minus y root t by 2 log 2, and finally minus 1 by 2 into minus plus log 2 by 2. I think I've got it right. Just to check, plus. Okay. And now a lot of things cancel out. These two go away. These two go away. And you are left with. Are we interested in y squared by 4t? Where does y squared by 4t come? Where did this one come? This one come from? This one. Is t by 2 into y squared by 2t? Where does it come from? No, my point is that this, I'm sorry. So this term I multiplied by y squared by 2. When I multiply t into this, there's no t here, sorry. Now I'm fine. Okay? Then what about this one? Y squared by 4. That also has a sign problem. Minus y root t by 2. This is minus y root t by 2 into log 2, it is plus. And this is plus y root t by 2. So these two also go away. Yeah. So all the terms, now I can take the limit t going to infinity, and many terms have dropped out. Okay. Let us hope I get the final answer right. Sorry?
In the next step.
Y squared by 4t.
That should be there.
Yeah, but we are going to take the limit t going to infinity and remove all of them.
So that goes to 0.
That goes to 0. So we have taken multiplied. So whenever we multiply and take the limit, we have chosen our y carefully. Y is finite. Then we are going to take the limit t going to infinity. Okay, so this becomes, so let me now be minus t log 2 minus half log of 2 pi minus half log t. If I don't get the right answer, then I'll just stop and write y squared by, this y squared by 2, this cancelled out this, minus y squared by 2. So I have done this one, I have done this one, I have done this one, and then there is a log 2. This t log 2 also gets cancelled out. So I must have done something in the. This minus 2t log 2, no? So that goes away. 2. So therefore, when I now take, so this is the logarithm. So if I take p of x, this becomes e to the power minus y squared by 2 by root of 2 pi t into 2 y squared by 2. Okay, if I want, I can substitute back y. Y is x squared by x by root t minus x squared by 2t. Oh, I should have not tried this, but anyway, it worked out fine. Okay, so this is my. So I did this calculation. If there's any, I don't think there's any error because it matches with this answer. Here I have not written a factor of 2. This 2 is missing here. But this, when I do the derivation, I get a 2. But this is a Gaussian centered about 0 with mean 2t or t. Expectation of x square is exactly t. But if I look at this expression, there's a factor of 2. So it's not normalized very well. So this 2 has to disappear. So you have to tell me why the 2 should not be there. It's not because of an algebraic error, but when the answer should not contain a 2. That is all I'm trying to say. Okay. So I will leave it to figure out why this 2 goes away. So let us now just summarize. So we took random variables whose distribution was either +1 or -1, added many of them together, and when I looked at the distribution of the sum, is a nice Gaussian. Okay. So this much we could do exactly, there was no issue. But yeah, but you may ask, so what? No, you did this calculation for a very specific problem of the random walk. So why spend so much time doing this? So let me now show. See, if I give you another problem where I say there's a random walker, but the random walker is now can take one step, not just one step, it can take +2 and -2 also. Then I cannot do this calculation. So if I want to ask for such a problem, what is my P of x? I have to do a simulation. I have to put in the computer and see what do I get. So this is what I will do. I will try to ask whether the answer we derived, this answer, has any meaning for a different problem. Is the motivation clear? So let me start with this random walk. This is we did. It can go +1, -1. This is a in 2 dimension. It can go left, right, bottom, left, and so on. Oops. Now, just to show that we have a formula which we did for large time, large t. If I do, so how do I do a simulation? So I put on a computer. I every time ask the computer to take a random number between 0 and 1. If the random number is greater than half, I make it move to the right. If it's less than half, I make it to the left. Then I do it for 8 time steps. It reaches some point, let's say at 8, -8 to +8. Then you do it some millions of times. And then you make a histogram of those runs and you ask how many times it reached 8, 6, 4, 2 and so on, and divide by the number of realizations you did. And then you get a P of xt. So what I have plotted here is the blue dots are from the simulation, what I call such a simulation is called a Monte Carlo simulation. And what is the red line? Red line is that Gaussian, e to the power minus x squared by 2t. Now even though we derived it for very large time, you can see for t equal to 8 itself, it is quite reasonable. If I do t equal to 12, it becomes even more reasonable. 16, I can barely distinguish between the two. Okay, so this is how the curve looks like for various times, 8, 12, 16, 20. It starts spreading out as root t. So if somebody asks you, how does the random walk distribution looks like? It's a Gaussian with increasing width, which increases the root. Okay, this is just to redo what I derived here. So now I want to test whether if I take a random walk with different rules, what is the relation to P of x? I have done, let's say, 1 million times. So this histogram is generated with a lot of averages. It becomes, every time I'll take 8 steps, I ask where is the particle, then I make the counter go up at that point by 1, then I do it for 1 million times.
In this slide, like t is equal to 16 has come a relatively lesser standard deviation than t is equal to 8.
No, it has come with more. If I look at 16, it's actually this blue.
Okay.
The red is 20, the purple is 20, the 16 is blue,
The
green is
scales are different. The x-axis is different, right? Like
here the x-axis, only if we scale the x-axis appropriately, we'll be able to figure out.
Got it.
Exactly, okay. So now I want to ask, what is the probability of large x? The probability it is at time point x, when the probability for small x, that -1 plus 1, is not simple. I cannot count, so I am going to do a Monte Carlo simulation. Oops. So I am going to choose the P of x, the step distribution, a more complex. So I've done 4 different choices. The first one is regular random walk, +1 or -1. The second one, it is allowed 0, +1, -1, -2, +2. The third one, I have not even chosen a discrete one. I chose continuous. Each time I take a Gaussian, I take some random number from there. It could be even as large as if it's continuous. It can be even answer could be as big as infinity. Okay. And the fourth one, again the step length is continuous, but the distribution is exponential. Is this clear? The 4 choices, but I need to compare between the 3 or 4 of them. So I have kept some parameters same. I have made sure that the mean is always 0 and the standard deviation is always 1. So whatever is your individual step size, I have kept these 2 parameters same for all of them, but the distribution is very different. Then I do the same. So this is the regular random walk, +1 or -1. And if I do, I think this is 120, so 20 steps, 20 step random walker, and I must have averaged again 1 million times, and you get a distribution like that. Now, if I do it for 5 step, you can take 0, 1, +-1, +-2. Then that's not even symmetric, it is asymmetric. This is more, this is less, and so on. And I do a simulation, and I get some data for that. I have not compared between the 2, but it looks something like this. Likewise, I do for a Gaussian. So the individual step length is taken from a distribution like this, continuous distribution, goes from -infinity to +infinity. Now, of course, your x also is discrete, but if you want to make a plot, you have to sort of discretize them. So I have discretized the plot into this one. And finally, I have chosen exponential distribution e to the power -x mod x, and there also the range is from -infinity to +infinity. You add up all of them and you get some answer like that. Okay. So this procedure is saying that I choose my individual step length from very different distributions, and I create the distribution for capital X after 20 steps. Next thing to do is plot them all together, and there is no difference between all of them. They are exactly the same. So plot together, and clearly they have no, it doesn't, the final answer does not depend at all on what is your individual step length. This red line that's plotted here is the answer I derived here for the simple random walk. Okay, so it is what one would call universal. Universal in the sense the final answer does not depend on what you put in at all. Okay. Even though this calculation some people have not done before, when you see on the computer first time, actually it is quite surprising. I myself was surprised that there is no difference between any of them. Is this plot clear? So you can also try this out with okay, you can also try this out. So then immediately the question arises, why this universality? Why should the final answer be universal when t becomes large? So then there are some results in, so I will go through now a bit, I'll just take the results so that it becomes clear. So let x1, x2, xn be a sequence of uncorrelated random variables with mean mu and variance sigma square. Example, +1, -1. x1 could be +1, -1, x2 could be +1, -1, and so on. Mean is 0 then, and variance is 1. But we have generalized it to general sequence. Then I am interested in the mean of that problem. I take the sum of all those variables and divide by n. Now the statement of law of large numbers is that if I look at this mean value, it has some mean value which is mu. If I look at the difference from mu, let's say is greater than some value, that probability is 0. What does it mean? It means that when n becomes larger and larger, then this average becomes mu. I cannot get any answer different from mu. I cannot, if the mean is 0, I cannot get 0.0001. I always get 0. As n goes to, somewhere I forgot n goes to infinity in this one. So this statement says that the probability that this mean value differs from mu is by a finite number is exactly 0. But you know that if I make a measurement in a lab, I don't get exactly always the same answer. I get some answer which is different. So what is the meaning of this this result? It says that the mean, your calculated mean tends towards mu. It does not tell you how it tends towards mu. It just says that when n goes to infinity, it just definitely tends towards mu, which is actually very intuitive. So the next result is the next result is to say that how does xn tend to mu, and that is called something called central limit theorem. So the central limit theorem says something. So the statement is about, you have again n variables, they are independent, identically distributed, which means they are taken in the same distribution with mean mu and variance sigma square. Now I will, before giving the result, I will motivate why it is. So this is exactly what we did for the random walk, right? But this is only now making a more abstract statement for that. So let us construct a variable y, which is x1 plus x2 plus xn, the sum of those random variables. I know that if I take the mean of y, it is n times the mean of x, which is mu times n. Mu is the mean. Okay, so since I know that answer, I am going to subtract that out. So I am going to redefine y, which is summation over this minus n times mu. Okay, and that mu, this n mu's I can distribute like this: x1 minus mu plus x2 minus mu plus xn minus mu. Okay, now this is my new definition of y. So now my y square becomes x minus x1, x minus mu the whole square plus x2 minus mu the whole square plus x3 minus mu, and so on. Okay. So like before, just like the random walk answer, this becomes n times the variance of one quantity, n times sigma square. Okay. So now I know if I subtract out the mean, the variance of y is n times sigma square. So I want to take this also out. So I am going to redefine y. Y is x1 plus x2 plus xn minus n times mu by sigma root n. So I am going to absorb this into definition of y. This is exactly what we did here. We decided that your x is going to be root t, the root 10. So I am going to define. Now I can ask, what is this distribution for p of y? So some derivation is there. I will skip the derivation because I'll skip the derivation. You can find this derivation in some keywords you know, you have to look at the cumulant generating function, but it's not important. You can do the derivation. So it says that, okay, so it says that if I look at p of y, it becomes a Gaussian like this, just like we derived here, independent of what is my distribution for the original x1, x2, xn. So let me now restate this result so that I don't make any error in the statement. So it says, let x1, x2, xn be IID random variables, each with mean mu and variance sigma square. Then the distribution for y, which is sum over xn, subtract out the mean, divide by the variance, then this y has a distribution which is a Gaussian, it's actually normal distribution, independent of what the distribution of x1 to xn are. And that is what we demonstrated by simulation as well as a calculation. Okay. So this is the central limit theory. It says that when the numbers become large, I don't care how the microscopic distributions are. And there's a word for this, this is called a stable distribution. Is this point clear? Any questions? Okay. So suppose now I know central limit theorem, and I am in a lab or in a running a computer program, and I take readings at regular intervals. I take the reading of, I don't know how many, what is the mass of uh, something, and I take n readings. I take reading x1, x2, xn. Then how do I take the mean value in a lab? I just add up all of them and take the mean. So when I add all of them by central limit theorem, what do I get? When I add a large number of them, I say this answer is typically the mean value of x, the actual value of x, mean value of x times n plus minus root n times the variance. That's what the central limit theorem said. But when I take the mean reading, I divide by n. When I divide by n, I get the mean value of x plus minus something by root n, the standard deviation by root n. So this is my error. So when I take the reading in a lab, I take the mean value, that is my measured value, and the error is 1 by root n times the standard deviation. So if I take more and more readings, my errors go down. That is why you have to take, and the readings go down in precisely this fashion. Okay. So but it is only root n. So if I do 10 to the power 6 readings and then I do 10 to the power 8 readings, I only get a factor of 0.1, one answer in the end. Okay. Okay. That is one. Second is, what is the connection to what we discussed before? We discussed things about density, pressure and so on. Where does the large numbers come in there? So for example, if I were to measure pressure, I put a probe there. I measure the collision of molecules with that probe. I measure the momentum change every time. I sum over this momentum change over a large number of particles, or large number of collisions, and then I ask what's the average. That average by what central limit theorem is a very well defined value. And so it is a sum of random numbers, and it tells you that you can tell that answer is exactly some number with very little error. Error going to 0 when the number of particles become large. Likewise, for density, we showed that when delta V becomes larger, then it is like saying to each particle I assign 1 if it is inside delta V, 0 otherwise. Then I sum over this 1 and 0. The answer is the number of particles, n is sum, if I call this xi, n is sum over I xi. But that also is governed by central limit theorem. It gives you a nice, which we derived explicitly using the Poisson distribution. Okay. So the central limit theorem plays a central role in telling you that it does not matter how the individual interactions are and how they are distributed. When you sum over a lot of them, they become universal and concentrated at the mean value. That is why in thermodynamics, when you are discussing E, energy, we are not discussing energy fluctuation. You can always tell E is this, but you know energy is fluctuating in a real system. But you can get away by saying talking only about the mean value. Okay. Similarly, if I want to measure energy, energy is related to the kinetic energy. The kinetic energy keeps changing. But when I sum over all those energies, they become well defined. Okay. So that is where I will. No, I had just to tell that things are not all nice. So I had one more slide as something for you to think about. So I showed explicitly that if I do for a random walk, I get a Gaussian. I did simulations for two-step Gaussian and so on. They all went to Gaussian. Is it always true? So now I do a simulation where your individual step length is now taken from something called a Cauchy distribution. The Cauchy distribution is P of x is a by pi into a square plus x square, x running from minus infinity to plus infinity. So every time I draw a random number x from this distribution, and a random walk makes that step, and vice versa, and not vice versa. It keeps doing that. I have done it for what is this 25, 50, 100. 25, 50, 100. Does not matter. What, twice I have plotted. It's some error. So I have plotted this for various n's, and when I look at the distribution, the sum of those variables is not a Gaussian. It is in fact the sum of the random numbers when I scale x by n happens to be a Cauchy distribution itself. So what went wrong? We proved there was a theorem which said that they must go to a Gaussian. But when I do with such a distribution, I don't get a Gaussian, I get a Cauchy, something else. What in the statement of the theorem did I violate? No, I am again taking independent distributions. As somebody pointed out, yeah, in this case, both the mean as well as the variance, both are violated. They are not finite. I cannot have that for the Gaussian, I needed finite mu, finite sigma square. In this case, I violated both, even if I violate one of them by making this x cube. Why does the mean diverge? When I do the integral over x times this one, for large x it is 1 by x, which diverges, the integral does not diverge. If I make it x to the power 5 by 2, then mean converges, but second moment diverges. Okay. So one must remember that the central limit theorem works only when mu and sigma are finite. When they are not finite, when they diverge, which is of what are called technically called Levy distributions, you must remember, or at least in your mind just feel that there are some other distributions which are stable, which happens to be those distributions themselves. Okay. So this is just we are not going to prove any of these things, but to keep in mind that it is possible to have, yeah, can we formalize this, can we formalize the observations that I leave as an exercise. Okay, and you may not come across these often, but it is good to know that sometimes you can violate these conditions. And yeah, so I will stop here. So just to say, so we spent some time today on mostly probability, but the description of systems with large degrees of freedom are probabilistic. So it's good to have some background of probability and its main results. Yeah.
Sir, you said that mean and standard deviation has to be finite. So is there any condition on, like, it should be 0 or something?
No, it should be finite number. So the only condition here would be that, if I have a distribution like this and I look at the large x behavior here, you should go faster than x cube. If it is faster than x cube, then the second moment everything will converge.
So in general, for a physical system, we just have to ensure that like things are finite. We can expect a Gaussian in general.
No, there are some systems where this is violated. It becomes interesting. Then you get some different behavior that you get. Yeah. Yeah, maybe with this point which an example can be discussed later. But if later on, if we come to that region, we'll discuss that. So I have tried to choose topics up to now, which doesn't require any background up to now. You can all follow this just with what you know. But next time I will try to do how to go through. Some of you have done StatMech, some of you have not done StatMech. But just summarize that given a system with microscopic interactions, how does one derive the macroscopic behavior? I will just give the working rules for that. For that also you don't need any background information, and then we will work with them. Okay.